Canada. Let's do. This is me, and I just want to recognize 3 collaborators there at the bottom: Matt, Boris, and Eve. Fantastic developers that work for me, but they're stuck at home working. So I'm going to talk about this thing called KTPI. It's a R library that I developed, open source library. I'm going to talk about why we developed it for our data modeling projects. I'm going to talk about the capabilities of KTPI, and just to give you a high-level overview of how we use KTPI at the scales that we need for our projects. Okay, so KTPI is one of the inputs to our spatial data machine learning. Within the forestry sector, we have this service called High Resolution Imagery Service, and it basically, from a training perspective, there's sample plots of trees, and pretty typical of the forest industry, where they've gone and measured everything about individual trees in a given area. And then on top of that, we have project scale indices that come out of LiDAR. They come out of high resolution color infrared imagery and multi-scale KTPI. And we train the model based on the sample plot versus the project level data. And we basically come up with what a tree looks like and what its growth is. And then we're able to impute species and productivity in other locations in the project, other project locations. Within the insurance industry, we have this municipal risk assessment tool. There's damage events, and then we have project scale data just created from municipal infrastructure indices, land use indices, as well as, again, multi-scale KTPI. We train it to know or to figure out what caused a damage event to occur, and then we can use that to predict damage events in other locations. But our challenge, which it is just developing these multi-scale KTPI indices at the scales we need them. So that's very CPU intensive. So what is KTPI? It's an R library. It's up on GitHub. It uses focal analysis of raster digital elevation data, and then it also uses zonal analysis of raster spatial feature data, and just derives indices related to statistic, terrain properties, topographic position indices, as well as more complex interaction indices between elevation and aspect. I used the work of Robert Heijman's raster terrain library, Andrew Weiss's topographic position indices, which were developed as an add-on to ArcGIS, an older version of ArcGIS. And I also used the work of Albert Stage, and he's the one that came up with these interaction indices between aspect and elevation. This is just an example of data, probably not that great, but on the right you can see DEM, and on the left side is feature data. This is one tile of the project. In a forestry project example, there's 218 tiles covering 5,000 square kilometers. Each tile contains 68,000 features. So it's polygon data rasterized based on a unique identifier. And within each one of these features, 68,000 within a tile, we calculate over 800 indices related to topography. This is just a statistic indice. You calculate the mean and the standard deviation within a given feature using zonal analysis. Pretty simple. This uses Robert Heijman's R raster library. One of them is roughness and the other one is slope. And again, you calculate it down to the zone of an individual feature. This one's a little more complex. This is where we start bringing in the kernel. Andrew Weiss's work on the topographic position. And first you do a focal analysis with a given kernel of difference from mean and standard deviation, and then you do a zonal analysis down to the feature. And the number of indices depends on the number of kernels you want to throw at this thing. So in our project, we start with 25 meters and we work all the way out to 2 kilometers, and go at more or less a 25 to 100 meter interval. This is based on Albert Stage's work of kernel aspect. Again, a focal analysis within a given kernel size around aspect and elevation, and then a zonal analysis down to the feature level. In our example of this forestry project, again, depending on the number of kernels you want to calculate, for those 218 tiles over that, whatever, 5,000 square kilometers, it would require running this KTPI tool 80,000 times. And this is where our challenge comes in. It takes about 1 CPU hour to process 10 square kilometers. So, like I was saying, for 5,000 square kilometers, 500 CPU hours. And this is where the help of those 3 gentlemen I worked with will come in soon. You could run a single CLI command. I use docopt within KTPI to develop the CLI, and so you can run one of them. You could run 80,000 of them if you wanted to. Or within KTPI, option 2 is there's a CLI command generator. So you can say, I want to run these functions over these tiles at these raster cell sizes, and it'll spit out all the commands that you would require to run those, and then you can supply them back into a KTPI. So, you know, as a bash script or whatever, but with these 3 developers, Matt, Boris, and Eve, we developed using Amazon SQS service and Amazon Elastic Container Service. Within KTPI, there's a tool to generate queue messages. And again, pick the functions you want to run, pick the tiles that you want to run this over, and pick the cell sizes and the kernels, and it'll spit out all the SQS messages. You then take those messages and push them up to an Amazon SQS queue. You have to get your data up to S3, and then you can configure your Elastic Container Services. I have the tools exist within the repo. They have to be customized for you, but there's tools that will allow you to start that Elastic Container Services. It'll allow you to push tasks to each container. It actually uses Docker, so just that helps with any dependencies. Again, that tool is there. You can actually start the task on the container. The container goes and retrieves the messages off of SQS. There's a client that does that, a JavaScript client. It downloads the message, generates the command, which also fetches data off of S3, runs the KTPI command, checks the outputs to see if they actually worked. If it didn't yet, what's great about SQS is the message will actually go back to SQS, so it could be tested again. And if it was successful, it writes the data to basically a CSV, you know, the indice for each feature, out to S3. This is the architecture. You can see the user over there puts the data S3, uses the SQS tool to generate the queue messages, puts them up to SQS, starts the tasks on the container service, and the container runs, pulls messages, gets data, writes data, and we have it outputting the logs all to Loggly. But just one thing about Loggly, it only keeps your data for a week, your logs for a week, so just be forewarned if you want to go back and see if something did not work for whatever reason, you have to do it within a week. So what's really helpful is moving to, I'm having this up on Elastic Container Service and using Docker. We've managed to make this process really scalable. SQS is a great repository for handling individual tasks. That dead letter queue within SQS. So if we have it set up so it'll try running a message 3 times. If it then fails, it gets output to a dead letter queue, and you can then go later and figure out why that particular task might have failed. Each one of the self-contained tasks sort of removes the limits on the area that we can actually run this over. So, all it requires is just more compute time. But 5,000 square kilometers, 10,000 square kilometers, it doesn't really matter. And we're currently working on a front end, user-friendly front end, that will allow our users, our less tech-savvy users, to use this, and it actually takes advantage of Amazon Spot instances. Those ones you can bid on for like a cheaper price, and it only starts them up when it's or uses them after it gets to that price. And I'm interested. Probably most of you attended the keynote this morning. There's that LOLA data, which is digital elevation data for the moon. I think it will be. I'm interested in putting some of that data onto this and just seeing what we can get out of it. But that is it. I have a few minutes left, but that's all right. Any questions that I could take from anyone? GitHub repo is up there. I can go back if anybody wants to see. Yeah. Sure. Yeah. So in this, on the left-hand side, it's basically what a feature is. What is a feature was the question, sorry. This slide over here we've segmented the forest into similarly sized polygon areas. There might be a whole group of trees, but we've then subdivided that into equal, fairly similar segment sizes. In this case, they're 18 meters by 18 meters, and that way it just makes having an equal aerial unit of analysis just sort of takes away any issues related to area weighting. But they are polygon areas. Each one of them has a unique identifier. In our 5,000 square kilometers, we had 12 million polygons. And with the zonal analysis, we can then go and, for every unique raster cell value, we can then go and calculate the terrain indices for that particular raster value. So we end up with 12 million records and over 800 attributes. Make sense? Okay. I can explain more details, and actually I think we did a relatively good job with the documentation up on GitHub. Yeah. Another question? Oh, I guess I'm out of questions. All right, done. Thank you.